This is physical chemistry. We're starting chapter 9, section 1. Chapter 9, we're talking about solutions. A solution is a homogeneous mixture. It can have several components, though. Now, as far as measuring solution composition, there are two categories. One is the temperature-dependent ones, and one is the temperature-independent ones. Now, examples of temperature-dependent ones, we have molar concentration. That's a C sub I, or I is the solute. So C sub I is defined as Ni over V, where N is the number of moles of our solute, and V is the total volume of the solution. This is the same thing as capital M, which is molarity. Another is the mass concentration, rho sub I, kind of like density actually. And again, I is our solute, the substance being dissolved. And that's just M sub I over V, where M is the mass, and so we're dividing mass divided by volume. And the mass could be measured in grams or kilograms, and the volume would be in like liters or meters cubed. The first one, it makes more sense, it's more common, more useful, easier for chemists. But the second one, mass concentration, if you do not know the number of moles you have, or you don't know the molecular weight of material, obviously you can't use molarity. So you use mass concentration for stuff like that. An example would be polymers. So you don't know how long the polymer has grown, the chain has grown. Now, as far as temperature-independent ones, there are a few of these. One, of course, is just mole fraction, X sub I, which we'll be using a lot in this chapter. X sub I is just N sub I over N total. So the number of moles of our solute divided by the total number of moles. Molality is the one lowercase m sub b, where B is our solute and then A is our solvent. So you just take the number of moles of our solute and divide it by the total weight of the solvent. And of course weight would be in kilograms usually. And then, let's see here, another way to calculate that would be to find the weight of your solute, your solvent. It's just the number of moles of the solvent times the molar mass, or molecular weight, of your solvent. So notice N over N, so it's a ratio. Continuing on physical chemistry, chapter 9, section 1, we're talking another example of a temperature-independent way of measuring concentration is the weight percent. The weight percent is found by the weight of your solute V divided by the total weight of your solution times 100%, of course. Like I said, B is your solute. This is a common way of doing it for stock chemicals. And this ratio right here, the weight of your solute divided by the total weight of the solution, is called the weight fraction. Now, we're going to talk about partial molar quantities. Let's say that we have our system, our solution, with a whole bunch of different substances. So substance 1, 2, 3, 4, all the way to R different substances. So N sub 1 would be the number of moles of substance 1, N sub 2 would be the number of moles of substance 2, N sub 3 would be the number of moles of substance 3, etc., all the way to N sub R, which would be the number of moles of substance R. Now we're going to say that Vm star is the molar volume of any pure substance. The star means unmixed. M, of course, means molar, and capital V is volume. So the star means pure substance, or it can be a collection of pure substances. Like you have a container of A separate from a container of B, or 1, 2, 3, etc. So V star, this is the total volume before mixing. V star is just found by adding them up because it's extensive. So you have the number of moles of 1 times the molar volume 1 unmixed, plus the number of moles of substance 2 times the molar volume of substance 2 unmixed, plus the number of moles of substance 3 times the molar volume of substance 3 unmixed, etc., all the way to the number of moles of substance R times the molar volume of substance R unmixed. And then without the star, V is just the total volume after mixing. Now we're going to find out in this chapter why, but generally speaking, the unmixed volume is not necessarily the same as the mixed volume, even if we're at constant temperature and pressure. For physical chemistry, chapter 9, actually starting with that letter B, we're in section 2 now. As an example of how V star is not equal to V, Let's say you mix 50.0 milliliters of ethanol and 50.0 milliliters of water. V star is just the 50 milliliters plus 50 milliliters, so you get 100.0 milliliters. But V, in practice, if you were to do this as an experiment, is only 96.5 milliliters. It's a little bit smaller. V cannot be greater than V star. There's several reasons for that. One is just because of intermolecular forces and how they're all attractive. And one, just because of molecular size and shape. This will make more sense later when we talk about how this happens. Now, of course, we already know other examples of extensive quantities would be entropy, Gibbs free energy, enthalpy, Helmholtz free energy, and internal energy. Now, so we know the volume is a function of temperature, the pressure, and all the different types of substances, constituents you have in our solution. And then likewise the Gibbs free energy would also be a function of the temperature and the pressure and all the different substances you have in the solution. So let's say, what's our exact differential of volume then? Then the differential of volume is going to be equal to the derivative of volume with respect to temperature, holding pressure and all the different substances constant, times the differential of temperature, plus the derivative of volume with respect to pressure, holding temperature and all the different substances constant, times the differential of pressure, plus the derivative of volume with respect to substance 1, holding temperature, pressure, and all other substances constant, times the differential of substance 1, etc., all the way to the derivative of volume with respect to the number of moles of substance R, holding temperature and pressure and all the other substances constant, times the differential of R, or the differential of number of moles of substance R. So we get partial molar volume then, is the V sub j. And that's equal to the derivative of volume with respect to N sub j, holding temperature, pressure, and all other substances constant. So each one of these is a partial molar volume. Other books you might just see it written as V bar is equal to molar volume. And that's just equal to the volume divided by the number of moles. Now let's say we graph this. We have volume over here, and then we have the number of moles of solute. Notice a shaped curve, so you have a minimum here. So you will have a concentration in which you'll have the lowest total volume of our solution. Continuing on physical chemistry, chapter 9, this is the end of section 2. So we have the partial molar the partial molar volume of substance I is just a function of temperature and pressure and the amount of each substance. Now, if we set the temperature equal constant temperature, so dT equals 0, constant pressure, so dP equals 0, then we just get the differential of volume is equal to the partial molar internal volume of each substance times the change in the number of moles of each substance when that substance is added. So in this case, J. So if we add more J, you take the partial molar volume of J times the amount of the change in the amount of J, and that'll be the change in the total volume. Now rewritten like we had it before, not assuming constant temperature and pressure then, remember the exact differential of volume would be dV equals the partial derivative of volume with respect to temperature, holding pressure and all substances constant, times the differential of temperature, plus the differential of volume with respect to pressure, holding temperature and all other substances constant, times the differential of pressure, plus the sum of all these different partial molar volumes, times the change in the number of moles of each substance. Now remember, we said before how V star, that's the total volume before mixing, and that's calculated by adding up the sum of the number of molecules times the molar volume of all those substances unmixed. And then V would be the total volume after mixing, which is the sum of the amount of substances times the partial molar volume of those. So the change in volume from mixing is just going to be equal to V minus V star. So we substitute those in, we get the sum of Ni VMI minus the sum of Ni VMI star. Remember, mixed minus unmixed. We can pull the Ni out and simplify, so we get the sum of the number of moles of substance I times the change in the molar volume from unmixed to mixing. And remember, we said before that volume is always less than the unmixed molar volume at constant temperature and pressure. Likewise, we also have the partial molar internal energy, which would be U I bar, and the partial molar enthalpy, which is H I bar. But the most important one, because remember when we talked about equilibrium or condition for equilibrium, G I bar is defined as the partial derivative of G with respect to the amount of substance I, holding temperature and pressure, and all other substances constant. And that, of course, would make it the same thing as mu sub I, our chemical potential. Continuing on physical chemistry, chapter 9, this is section 3. This is everything of section 3 we're going to talk about. There are basically different types of mixing quantities, quantities that change when you mix them. For example, there's the change in Gibbs free energy of mixing, and that's defined as just the Gibbs free energy before, or the Gibbs free energy after minus the Gibbs free energy before. Remember, star means unmixed. Same way we get a change in S, entropy of mixing, and that's just the S final minus S initial, where remember star is the unmixed. Now we know from a long time ago that delta G is equal to delta H minus T delta S at constant temperature only, obviously. So delta G mix is going to be equal to delta H mix minus T delta S mix. Now, some of the changes are due to the intermolecular forces, and some of them are due to intermolecular forces and also entropy. For example, the change in volume of mixing, the change in internal energy of mixing, the change in enthalpy of mixing, and the change in heat capacity of mixing, those are all due just to intermolecular forces. But the change in S of mixing is obviously due to entropy, and the change in Gibbs free energy of mixing and the change in Helmholtz free energy of mixing is due to entropy and the intermolecular forces. Okay, this is physical chemistry, chapter 9. We're in section 5 right now. We're going to talk about ideal solutions in the liquid or solid phases. Now, before mixing, let's say we have substance A and B. So A and A, they're going to have some sort of type of molecular bond to each other, because we're not talking about a gas, we're talking about a liquid or solid, so there'll be intermolecular forces. And likewise, there'll be some sort of intermolecular forces between B and B. If the intermolecular forces between A and A is the same as between B and B, then, and if that's the same as A to B, then that, and if they have the same structure, then the solution is an ideal solution. Now, one example is a solid solution of copper and zinc. Now, other examples, let's say we have iodomethane with either 12 carbon or 13 carbon. It's the same substance, really, almost identical, just a different isotope of carbon. So that's close enough, and that would be an ideal solution. Likewise, let's say we have benzene and toluene. Again, this one little methyl group doesn't really change the overall size and shape and so on of the substance overall. So that would be an ideal solution too. And then let's say we have chloroethane and bromoethane. Well, obviously, chlorine and bromine aren't identical. They're a little bit different, but overall the molecules are similar enough that we could call a mixture of those two to be an ideal solution. Now, on the other hand, there are two ways that we wouldn't have an ideal solution. One is, let's say we have the intermolecular forces between A and B and B are not the same as A and B. Or likewise, let's say that the size and shape of molecule A is not the same as the size and shape of molecule B. Now let's talk about what is the thermodynamic definition of an ideal solution. Well, for an ideal solution, one, we know that the change in Gibbs free energy of mixing is just going to be equal to RT, remember that's the gas constant and the absolute temperature, times the number of molecules of A times the natural log of the mole fraction of A, plus the number of moles of B times the natural log of the mole fraction of B. Now we know that the change in internal energy of mixing will be equal to 0, and the change in the volume of mixing is going to be equal to 0. Now we know that the change in enthalpy of mixing is going to be equal to the change in internal energy of mixing plus pressure times the change in change in volume of mixing. This is 0, and this is 0. Therefore, change in enthalpy of mixing is also equal to 0. Continuing on physical chemistry, chapter 9, this is section 5. So, state 1 is our unmixed state. We have substance A at temperature and pressure separated from substance B at temperature and pressure within our system. We let them mix together, so we get substance A plus substance B at the same original temperature and pressure. Now, remember, this is only true if A and B are roughly the same size and shape and have similar intermolecular forces. Now, delta S is equal to S2 minus S1. So the change in entropy is equal to entropy in state 2 minus the entropy in state 1. That's just the definition of change, or delta. And that's equal to K times the natural log of P2 over P1. So K, of course, is the Boltzmann constant. P2 is the probability, not the pressure of state 2, divided by the P1, which is the probability, not the pressure of state 1. Remember way back, I think, chapter 2, when we talked about absolute entropy and how those probabilities work. Now remember, we're using the superscript star or asterisk to mean before mixing. So let's say we have VA star, so that's the volume of substance A unmixed, divided by the total volume. And we're assuming ideal solution, so the star and unstarred are going to be the same. So this volume is going to be equal to VA star plus VB star. So this ratio is just the same as VA star over VA star plus VB star. And again, because we're assuming ideal solution, so there is the delta V is equal to 0, then we also get VA star over VA plus VB. Now, if you take this and use your ideal gas law, you can also derive that delta S is equal to the number of moles of A times R times the natural log of total volume divided by the volume of A, plus the number of moles of substance B times R times the natural log of volume divided by the volume of substance B. But again, this would only be true for an ideal gas, because obviously we used PV equals nRT. Now delta S mixing for liquid mixtures, it's going to be like this. If you flip this upside down, you get a minus sign. So we're going to get minus NAR, natural log of VA star over V, minus NBR, natural log of VB star over V. And again, this is only an ideal solution, which is our mixture. Continue on physical chemistry, chapter 9, this is section 5 still. So, since we're saying that molecules A and B have the same size, roughly, and similar intermolecular forces, and the same shape, roughly, then we know that the molar volume of A, unmixed, is equal to the molar volume of B, unmixed. And we know the molar volume of A, unmixed, is equal to the number of moles of A times the molar volume of A, unmixed. And the volume of B, unmixed, is equal to the number of moles times the molar volume of B, unmixed. Now we know that the total volume, then, is going to be equal to the volume of A, unmixed, plus the volume of B, unmixed. Because, again, we're assuming the same. So VA is the same as VA star, and VB is the same as VB star. So that's going to be equal to the number of moles of A plus the number of moles of B times the molar volume of A star, because they have the same molar volume here. That's what we did here. Or, likewise, the number of moles of A plus the number of moles of B times the molar volume of B star, since they're the same. Now, the change in entropy of mixing, we showed before, is minus R times the number of moles of A times the natural log of the mole fraction of A, plus the number of moles of B times the natural log of the mole fraction of B. And that's going to be at constant temperature and pressure only. Now, the change in mixing then, if we write in the mole fraction here, from what we've got up here, it's going to be minus Na times R times the natural log of the number of moles of A times the molar volume of A unmixed, divided by the total volume, which we found up here is just Na plus Nb times the molar volume of A unmixed. And then likewise, we're going to subtract out the number of moles of B minus R times the natural log of number of moles of B times the molar volume of B unmixed, divided by the total volume. Notice we use A in both sides, even though we got B up here. Now, the change in Gibbs free energy of mixing is going to be delta H, change in enthalpy of mixing, minus temperature times the change in entropy of mixing. Now we know that the delta H mixing of 0 is going to be equal to 0 for an ideal solution because the intermolecular forces between A and A or B and B are all the same. So any bonds that we break by adding B is going to be equal to the new bonds formed by adding B. Now delta G mixing then is going to be equal to 0 minus temperature times what we had for entropy of there, which is minus Na times R times the natural log of mole fraction of A, minus the number of moles of B times the gas constant times the natural log of mole fraction of B. Again, that's only for an ideal solution because of the approximations we made. So since just distributing it out our double negative, we get that the change in Gibbs free energy of mixing is equal to the gas constant times the absolute temperature times the number of moles of A times the natural log of the mole fraction of A plus the number of moles of B times the natural log of the mole fraction of B. And again, this is only for an ideal liquid or solid solution. Okay, physical chemistry, chapter 9, we're in section 5 still. Now, remember we talked before about R, the gas constant, and the way to calculate it is multiplying Avogadro's number times Boltzmann constant. So R is equal to capital N subscript A times lowercase k. Now, one way to look at these numbers is that R is the energy per mole, while K is the energy per atom or molecule. Now, another way to find R is if you take the limit as pressure approaches 0 of PV divided by NT. Now mu sub I, remember, we talked about before, is chemical potential. Now the change in Gibbs free energy of mixture is just the Gibbs free energy after mixing minus the Gibbs free energy before mixing. Remember the star is unmixed, and without the star you assume it's mixed. So for a pure substance, we get the Gibbs free energy of substance I, molar, is equal to the chemical potential mu sub I for that substance I. And that's equal to the Gibbs free energy of substance I total divided by N, the number of molecules of I, or the number of moles of I. So what we have is the delta G mixture, the change in Gibbs free energy from mixing, is equal to the sum of Ni mu sub I minus the sum of Ni mu sub I star. So again, that's mixed minus unmixed. And that's going to be equal to RT times the sum of Ni times the natural log of the mole fraction of substance I. Now we know that the sum of Ni mu sub I is equal to the sum of Ni times mu I star plus RT natural log of the mole fraction of I. So we get mu sub I is equal to mu I star plus RT times the natural log of the mole fraction of I. Now, remember though, mu sub I star, that's a function of temperature and pressure. So mu sub I is really mu sub I star as a function of temperature and pressure plus the gas constant R times the absolute temperature times the natural log of the mole fraction of I. Now this formula right here, this is our thermodynamic definition of an ideal solution. Another way to put it, a solution is ideal if the chemical potential of every single component in the solution obeys this equation for all solution compositions, in other words, any mole fraction I, 0 to 1, and for a reasonable range of temperature and pressure. Continuing on physical chemistry, chapter 9, this is the end of section 5. So what we showed before for mu and so on. So remember, our definition of ideal gas was that PV is equal to nRT. Now let's say we graph mu sub I against the mole fraction of substance I. So here's our zero line, positive, negative, no particular scale. So the maximum is where we have pure substance I, or a mole fraction of 1. If you have less of it, you're going to have less and less, lower and lower mu potential. In fact, as you get to 0 mu sub I, the chemical potential mu sub I is going to approach negative infinity. Continuing on physical chemistry, chapter 9, we're in section 6 right now. We've actually been in section 6 a while, but anyway. Thermodynamic properties of an ideal solution. Now remember, an ideal solution is a hypothetical model, kind of like an ideal gas. It's a mathematical convenience. Now remember the standard states we've already talked about before. The standard state for a gas is that pure ideal gas. The pressure naught is 1 bar, and the temperature can be whatever temperature of interest we have. Likewise for a liquid, it's a pure liquid. Our P naught is 1 bar, and the temperature is just the temperature of our solution, which can be abbreviated T subscript SOLN for solution. And then, of course, for a standard state for a solid is the pure solid, P naught at 1 bar again, and again our temperature is whatever temperature solution we happen to have. Now, mu I star, remember, is the chemical potential of the pure substance I. Star means unmixed. Mu I naught is equal to mu I star at temperature and pressure. Remember, naught means standard state, 1 bar, etc. So, and again, mu I star means pure substance. Mu I is equal to mu I star plus RT times the natural log of x sub I for an ideal solution. That was our definition we talked about before. Mu I naught is equal to mu I star at temperature and pressure for an ideal solution. We already mentioned that before. Okay, we're in physical chemistry, chapter 9, section 6 still. Nice big section. So part B, now we're going to talk about different mixing quantities. Now remember, we said before, the change in Gibbs free energy of mixing is equal to the Gibbs free energy after mixing minus the Gibbs free energy of the pure substance, or unmixed. Remember, star means pure, or unmixed. So the change in Gibbs free energy from mixing is equal to the sum of the number of moles of substance I times the Gibbs free energy molar of substance I mixed minus the Gibbs free energy molar unmixed. And that's assuming constant temperature and pressure, obviously. Now remember, the Gibbs, well, that's because the molar Gibbs free energy is just equal to the Gibbs free energy divided by the number of moles. So we substituted that in up here. So the Gibbs free energy of mixing is equal to the sum of the number of moles of substance I times the chemical potential of substance I mixed minus the chemical potential of substance I unmixed. That's we showed before where that mu is equal to the molar G. So doing this, we get mu sub I minus mu sub I star is equal to RT times the natural log of x sub I, mole fraction of I. So the delta G, change in Gibbs free energy from mixing, is equal to RT times the sum of the number of moles of substance I times the natural log of the mole fraction of substance I. And this is assuming we have an ideal solution and we're at constant temperature and pressure. Now remember, by definition, the mole fraction is going to be between 0 and 1. Obviously, if it's 0, it wouldn't be there at all. And if it was 1, we'd have a pure substance still. So we're going to ignore those two cases. So what that means is the natural log of the mole fraction is going to be always negative. So what that means is that this delta G mix term is always going to be less than 0. Therefore, mixing is always spontaneous. Now, the change in volume from mixing, we have the derivative of the change in Gibbs free energy of mixing divided by or with respect to pressure, holding temperature and the number of moles constant. Now, delta G mixing is independent of pressure at constant temperature. So what we got is the change in volume of mixing is equal to 0, and that's assuming an ideal solution and we're at constant temperature and pressure. Continuing on physical chemistry, chapter 9, section 6. So we have delta S mix is equal to minus the derivative of the Gibbs free energy of mixing with respect to temperature, holding pressure and the number of moles of substance I constant. So that's the derivative with respect to temperature of RT times the sum over I of the number of moles of I times the natural log of XI. So we get delta S mix is equal to minus R times the sum over I of Ni times the natural log of Xi, and that's for an ideal solution. Now, delta S mix is greater than 0, so entropy is rising with mixing, normally though. But a counterexample would be, let's say we have trichloromethane, or chloroform, whatever, and mixing that with acetone, which is this here, dichloroketone, or dimethylketone, whatever you call it. Anyway, so in that case, the change in entropy is actually less than 0, but the change in Gibbs free energy is still less than 0, so this mixing is spontaneous. Now remember, the change in enthalpy from mixing is just equal to the change in Gibbs free energy from mixing plus the absolute temperature times the change in entropy from mixing. So we get the delta H mixing is equal to RT times the sum over I of Ni natural log of Xi minus RT times the sum over I of Ni natural log of Xi. These two are the same terms, they cancel out and make 0. So for an ideal solution, the change in enthalpy of mixing is equal to 0. Or put another way, there's no heat of mixing. It's not endothermic or exothermic. Now here's an example of mixing something. So if you're mixing it with different mole fractions, notice B going from 0 to 1, or A going from 0 to 1. So you add them together, the delta H mixing is equal to 0, that's the horizontal line. But T delta S, it goes up and then it comes back down. And likewise delta G mixing, it goes down and it comes back up. So what this should show you is that, well, delta G gets minimized here, so spontaneous to, I didn't draw it very well, but it'd be half and half, assuming A and B are roughly identical. Physical Chemistry, Chapter 9, we're continuing Section 6. So delta S, remember, is in joules per mole Kelvin. So if you multiply that by absolute temperature in kelvins, T delta S, you get joules per mole. As an aside, there's a lot of gold dissolved in the ocean. It's not pure gold particles or anything like that. It's in the form of gold chloride. So the change in enthalpy of mixing, remember, is just the change in internal energy of mixing plus pressure times the change in volume of mixing, assuming we're constant pressure, obviously. Now we've shown that the change in enthalpy of mixing is equal to 0, and that the change in volume of mixing is equal to 0. So solving for the change in internal energy of mixing, we get that is equal to 0 also. And again, we're assuming that's an ideal solution though. Now, if the change in enthalpy of mixing is equal to 0, and the change in volume of mixing is equal to 0 though, that isn't really enough to prove that we have an ideal solution. Now, let's talk about vapor pressure for gas above a liquid solution, ideal solution. Now, we know for any gas that the partial pressure of substance I is equal to the mole fraction of substance I times the total pressure in the gas. Now, remember our condition for phase equilibrium is that the chemical potential I in the liquid phase is equal to the chemical potential I in the vapor phase. Remember, we're going to use V for vapor, not G for gas. So this is what our equilibrium looks like. We have our system, we have the liquid phase on the bottom, the gas phase on the top. So we have the mole fraction of substance 1 in the vapor phase, mole fraction of substance 2 in the vapor phase, mole fraction 3 in the vapor phase, etc., however many you got. And likewise, we have a mole fraction of substance 1 in the liquid phase, which could be different from the gas phase. And then we have the mole fraction of substance 2 in, oh, that is a 2. Okay, mole fraction of substance 2 in the liquid phase, and mole fraction 3, etc. We also know that the total pressure in the system is calculated just by adding up the pressure of the separate gases. So the pressure of substance 1, pressure of substance 2, pressure of substance, etc., all the way to pressure of substance I. So the total pressure, P, is just another name of saying piece of total. Now remember, the chemical potential of substance I in the liquid phase we showed is equal to the chemical potential I in the liquid phase unmixed plus RT times the natural log of the mole fraction of substance I in the liquid phase. That's assuming ideal solution. Likewise, the chemical potential of substance I in the vapor phase is equal to the chemical potential I in the vapor phase at standard pressure plus RT times the natural log of the partial pressure of substance I divided by P naught, which is 1 bar. And again, that's assuming we have an ideal gas mixture. Continue on Physical Chemistry, Chapter 9, Section 6. We're going to derive something now. So we're going to number a couple of equations for future reference. So the first equation, 1, we got mu sub I in the liquid phase, unmixed, plus RT times the natural log of the mole fraction of I in the liquid phase. That's going to be equal to mu I in the vapor phase at standard pressure, or standard state, plus RT times the natural log of the partial pressure of I over P naught. This is supposed to be a 0. So that's basically, we're setting mu sub I in the liquid phase, unmixed, at temperature and pressure I, unmixed, is equal to mu I in the vapor phase, unmixed, at temperature and partial pressure of I. Then the second equation we're going to use is this mu I liquid unmixed at temperature and partial pressure unmixed is equal to the chemical potential I in the vapor phase at specified temperature unmixed plus RT, natural log of the partial pressure of substance I divided by P naught. Now we're going to multiply this one by -1, so we'll get minus V sub I liquid unmixed minus RT, natural log of the mole fraction in the liquid phase, equal to minus the chemical potential of substance I in the vapor phase, standard state, minus RT, natural log of the partial pressure of I over P naught. Now we're going to add that to number 2, and that'll give us all this. So we get chemical potential I in the liquid phase unmixed at temperature and partial pressure I unmixed minus the chemical potential I in the liquid phase unmixed minus RT times the natural log of the mole fraction of I in the liquid phase. All that is equal to mu sub I in the vapor phase at temperature, the standard state, plus RT times the natural log of partial pressure of I unmixed over P naught, 1 bar, and minus the chemical potential of I in the vapor phase at standard state, minus RT natural log of partial pressure of I divided by P naught. Now, we know at lower moderate pressures we can say that the mu I liquid at temperature and pressure I unmixed is equal to mu I liquid at temperature and pressure. So we're just assuming that pressure is not going to make that much difference because it's the condensed phase. So what we get, simplifying this, using this, we get minus RT natural log of xi mole fraction of I in the liquid phase is equal to RT times the natural log of partial pressure of I unmixed minus the natural log of P naught minus the natural log of P sub I minus natural log of P naught. Now, we can further simplify this and say, well, we can divide both sides by RT. So, what we get is that minus natural log of x sub I liquid equals natural log of P sub I unmixed divided by the partial pressure of I. Okay, continuing on physical chemistry, chapter 9, section 6. So equation, we're going to number a couple equations for use reference because they're important. So 1, we have the chemical potential of I in the liquid phase unmixed plus RT, natural log of mole fraction of I in the liquid phase. That's equal to mu sub I in the vapor phase at standard pressure or standard state plus RT times the natural log of the partial pressure of I over P naught. And that's because basically what we've done here is taken the mu sub I liquid unmixed at temperature and the partial pressure of I unmixed and set it equal to the mu sub I chemical potential of I in the vapor phase unmixed at temperature and partial pressure of I. And then the other equation we're going to use, we're going to say, okay, mu sub I in the liquid phase unmixed at temperature and partial pressure of I unmixed. That's equal to chemical potential of I in the vapor phase at the specified temperature unmixed plus RT times the natural log of partial pressure of I over P naught. Now we're going to take our first equation, multiply it by -1, so all we're going to get is minus mu sub I in the liquid phase, unmixed, minus RT, natural log of mole fraction of I in the liquid phase, and that's equal to the chemical potential of I in the vapor phase at standard state, minus R times the temperature times the natural log of the partial pressure of I divided by P naught. Now we add that to our equation 2, and it gives us all this. The mu sub I in the liquid phase, unmixed at temperature and partial pressure I, unmixed, minus mu sub I in the liquid phase, unmixed, minus R times the absolute temperature times the natural log of mole fraction of I in the liquid phase. All that is equal to mu sub I in the vapor phase at the specified temperature, standard state though, plus R times the absolute temperature times the natural log of partial pressure of I unmixed divided by our standard pressure of 1 bar, minus the chemical potential of I in the vapor phase at standard state, minus R times the absolute temperature times the natural log of partial pressure of I divided by P naught. Now, at low to moderate pressures, we'll say that mu sub I in the liquid phase, unmixed, and temperature and partial pressure of I, unmixed, is going to be equal to mu sub I in the liquid phase, unmixed, at temperature and pressure. So, using that, we'll simplify and get minus RT times the natural log of mole fraction of I in the liquid phase is equal to RT times the natural log of partial pressure of I unmixed minus natural log of partial pressure of standard state, or well, 1 bar, minus natural log of p sub I plus natural log of p bar. These two cancel out. And then converting these two to a fraction using your log rule, and then dividing by everything by RT, you get minus natural log of the mole fraction of I in the liquid phase is equal to the natural log of the partial pressure of I unmixed divided by the partial pressure of I in the mixed. Continuing on physical chemistry, chapter 9, section 6. So last slide we showed the negative natural log of the mole fraction of I in the liquid phase is equal to the natural log of the partial pressure of I unmixed divided by the standard pressure. Then just multiply by -1 and flipping this upside down to get rid of the minus sign, we get the natural log of the mole fraction of I in the liquid phase is equal to the natural log of the partial pressure of I divided by the partial pressure of I unmixed. Now remember, the mole fraction of I in the liquid phase is equal to the partial pressure of I divided by the partial pressure of I star. We just took e to both sides here. So multiplying by pi star, we get partial pressure of I is equal to the mole fraction of I in the liquid phase times the partial pressure of I unmixed. This equation here is called Raoult's law for ideal solutions, and it's valid roughly from low to moderate pressure. Now, Pi, the partial pressure of I, is equal to Xi in the vapor phase times the total pressure. P is total pressure in the system above your ideal solution. So, setting these two equal to each other, because we're at equilibrium obviously, we get the mole fraction of I in the vapor phase times the total pressure is equal to the mole fraction of I in the liquid phase times the partial pressure of I unmixed. Now, let's do this for a two-component system. We're going to say we have component A and component B without being more specific. Now, we're going to say these two form an ideal solution here. So we know that the pressure total is just equal to the pressure of A plus the pressure of B. And we know that's equal to the mole fraction of A in the liquid phase times the pressure of A unmixed plus the mole fraction of B in the liquid phase times the pressure of B unmixed. Now, since there's only two components, remember, the mole fraction of B has to be equal to 1 minus the mole fraction of A. So using that, we say the total pressure is equal to the mole fraction of A in the liquid phase times the partial pressure of A unmixed plus 1 minus the mole fraction of A in the liquid phase times the partial pressure of B unmixed. Then just distributing that out, we get the pressure is equal to the mole fraction of A in the liquid phase times the partial pressure of A unmixed plus the partial pressure of B unmixed minus the mole fraction of A in the liquid phase times the partial pressure of B unmixed. Then we want to combine or factor out the mole fraction of A here. And the reason is we're going to get this in a form y equals mx b so we can graph it as a straight line. So we get the pressure above the solution is equal to the partial pressure of A minus the partial pressure of B times the mole fraction of A in the liquid phase plus the partial pressure of B unmixed. Continuing on physical chemistry, chapter 9, we're in section 6 now. So we showed to get the formula in the form y equals mx plus b, we get the pressure of the solution is equal to the partial pressure of A unmixed minus the partial pressure of B unmixed times the mole fraction of A in the liquid phase plus the partial pressure of B unmixed. Now, if we have the mole fraction of A in the liquid phase is equal to 0, then the pressure of the solution is going to be just equal to the pressure of B unmixed. If the mole fraction of A in the liquid phase is equal to 1, then the pressure of the solution has got to be equal to the pressure of A unmixed. So what we have here is a graph of the total pressure above our solution from 0 to whatever, and against the mole fraction of A in the liquid phase, remember. So we have two lines here. One is from A going from 0 to 1, or mole fraction. So this is going to go up to the partial pressure of A unmixed. So this line here is the pressure of A, partial pressure of A, which is equal to the mole fraction of A in the liquid phase times PA star. Likewise here, we're starting out with the partial pressure of B unmixed and going down to 0. This line is the partial pressure of B, which is equal to the mole fraction of B in the liquid phase times the partial pressure of B unmixed. The total pressure in the solution is just A plus B, which is another straight line. Now notice the way I drew this higher than that. So this is just the scenario in which the partial pressure of B unmixed is less than the partial pressure of A unmixed. It could be the other way around, or they could be equal to each other, but it'll work out roughly the same. So these are the three functions that we plotted. The pressure of the solution, which is equal to the partial pressure of A unmixed minus the partial pressure of B unmixed times the mole fraction of A in the liquid plus the partial pressure of B unmixed. And then we also graph the partial pressure of A, which is equal to the mole fraction of A in the liquid times the partial pressure of A unmixed. And then we also graph the partial pressure of B, which is equal to the mole fraction of B liquid times the partial pressure of B unmixed. Now, one example of a solution that is close to ideal is just benzene and toluene. Because benzene, as you know, is just a six-sided ring, and then toluene is the six-sided ring with the methyl group added to it. Both are planar though. Substitute pressure is equal to the mole fraction of A in the liquid phase times the partial pressure of A unmixed plus the partial pressure of B unmixed minus the mole fraction of A in the liquid phase times the partial pressure of B unmixed back into that equality we had before, where the mole fraction of I in the vapor phase times the total pressure is equal to mole fraction of I in the liquid phase times the partial pressure unmixed. And then we're going to solve for the mole fraction of A in the vapor phase. So we get mole fraction of A in the liquid phase times the partial pressure of I unmixed divided by all of this, the partial pressure of A minus the partial pressure of B, both unmixed, times the mole fraction of A in the liquid phase plus the partial pressure of B unmixed. Now this is not a straight line, except in the possibility that the partial pressure of A unmixed happens to be the partial pressure of B unmixed. Continuing on physical chemistry, chapter 9. This is the end of section 6. So I showed before how you can find that the mole fraction of substance A in the vapor phase for a two-component system is equal to the mole fraction of A in the liquid phase times the partial pressure of A unmixed divided by the partial pressure of A unmixed minus the partial pressure of B unmixed times the mole fraction of A in the liquid phase plus the partial pressure of B unmixed. And I said that this will not be linear unless, of course, that partial pressure of A and partial pressure of B just happen to be equal to each other, which is not necessarily the case at all. So here we have the graph of mole fraction versus mole fraction. Notice this is for the vapor phase, this is for the vapor phase, liquid phase. So here we have a straight line. This is the case I told you about in which PA unmixed is equal to PB unmixed. So this is a straight line. If PA is greater than PB, such as 3 times higher, then it's going to bulge outwards, up this way, which means you're going to have more mole fraction of A in the vapor phase than you would if you had in the liquid phase. On the other hand, in this case, where the partial pressure of A unmixed is only 1/3 of the partial pressure of B unmixed, then it's going to go down this way, which means that the mole fraction of A in the vapor phase is going to be less than you got for the mole fraction of A in the liquid phase. Continue on physical chemistry, chapter 9. This here is all we're going to do of section 7. We're talking about ideally dilute solutions. So an ideal solution, this solution exists in the limit where the molecules of the different components resemble one another very closely without actually being identical. And 2, an ideal dilute solution or an ideally dilute solution, the solvent mole fraction approaches 1 and the amount of solute present is very small. Now we're going to say capital A is the solvent, lowercase I is the solute. So if we have mu sub A is equal to mu sub A star at temperature and pressure plus RT natural log of XA, then we'll say the solvent is an ideally dilute solution. If we have mu sub I is equal to mu sub I standard temperature and pressure, plus RT natural log of Xi, then we'll say the solute is an ideally dilute solution. Now, if we have an ideally dilute solution, then we can use our different types of concentrations interchangeably. We'll say that the mole fraction of I is roughly equal to the molality of I, which is roughly equal to the molarity of I. Obviously, they won't be identical numbers, but they'll be on the same order of magnitude, so it'll be close enough. Continuing on section Physical Chemistry, Chapter 9, we're in section 8 now. So mu sub I is equal to mu sub I naught at temperature and pressure plus RT times the natural log of X sub I. And we said before that we're using such low concentrations, instead of X sub I, we could put in M sub I or C sub I, and it would work out the same. So let's talk about vapor pressure in our ideally dilute solution. We have our system, we have a liquid solution at the bottom, we're saying it's ideally dilute, and then of course we have vapor above it. Now, P sub I, remember, is the partial pressure of our solute, which is I, in the vapor phase, obviously. And P is the total pressure in the vapor phase. Now, mu sub I vapor is equal to mu sub I vapor at temperature in standard state plus RT times the natural log of the partial pressure of I divided by standard pressure. And that's for an ideal gas mixture. And then the chemical potential I in the liquid phase is equal to the chemical potential I in the liquid phase at standard state plus RT times the natural log of the mole fraction of I in the liquid phase. And that's in your solution. Now, at equilibrium, we know that the chemical potential I in the liquid phase is equal to the chemical potential I in the vapor phase. And given that, we can say a lot of things. One, that the mu sub I in the vapor phase naught plus RT natural log of P sub I over P naught is equal to the mu sub I in the liquid phase at naught plus RT times the natural log of the mole fraction of I in the liquid phase. Now we want the chemical potentials on one side, so we get the chemical potential of I in the liquid phase in standard state minus the chemical potential of I in the vapor phase in standard state, and that's equal to minus RT times the natural log of I in the liquid phase plus RT times the natural log of partial pressure of I divided by the standard partial pressure. Now we're going to divide both sides by RT, so we get the mu sub I in the liquid phase in standard state minus the mu sub I in the vapor phase in the standard state divided by RT, and that's going to be equal to the negative of the natural log of the mole fraction of I in the liquids plus the natural log of partial pressure of I divided by P naught. Continue on Physical Chemistry, Chapter 9, Section 8. So, continue what we were doing on the previous slide. We get mu sub I in the liquid phase, standard state, minus mu sub I in the vapor phase, standard state, divided by RT is equal to the natural log. We combine the different natural log terms. So we get Pi over mole fraction of I in the liquid phase times P naught. Now, we're going to take E to both sides and switch them around. So we get P sub I over mole fraction of I in the liquid phase times P naught is equal to E to the mu sub I in the liquid phase, standard state, minus mu sub I in the vapor phase, standard state, over RT. Now we're going to multiply by P naught, so we get this fraction Pi over mole fraction of I in the liquid phase is equal to P naught times E to the mu sub I in the liquid phase, standard state, minus mu sub I in the vapor phase, standard state, over RT. All this is equal to K sub I, which is dependent on temperature and pressure. So we get Pi over XIL is equal to Ki as a function of TB. Ki is called Henry's law constant. P sub I then is equal to Henry's law constant times the mole fraction of I in the liquid phase. This is Henry's law. Henry's law is used for dissolving gases and liquids. Its solute, remember, is only when you're in ideally dilute solution, in ideal vapor. It's used when you carbonate liquids, like soda for one thing. Remember, and of course it only applies to a closed system, such as a can of soda. Now, increasing pressure means that the mole fraction of I is going to increase, and therefore the solubility is going to increase. Now, X sub I is dimensionless, it's just a ratio. So K sub I is going to have units of pressure. Now for hydrogen, diatomic of course, as a solute, In water, it's 71.7 kilobars, but in benzene, it's 3.93 kilobars. Now, XLI liquid is equal to PI over KI. We just rearranged this formula. So the KI is on the bottom, which means the higher KI means lower solubility. Continuing on physical chemistry, chapter 9, section 8. So if we have increasing temperature, that means we're going to have decreasing mole fraction of substance I, and therefore decreasing solubility when we have H2O as the solvent. But the reverse will be true for organic solvents. Now, let's talk about variation of gas solubility with temperature. Now, normally, as temperature increases, then stability decreases. Now, one thing to keep in mind, though, Henry's law does not apply if you have strong electrolytes, such as hydrogen chloride gas. If you have H2O, water, as liquid as your solvent, and you try to dissolve hydrogen chloride gas, what's going to happen is you're going to make hydrochloric acid. So you get your hydronium aqueous ions and your aqueous chloride ions. Now, Henry's law, it also does not apply when the solute, the gas, reacts with the solvent. Now, remember we showed before, the partial pressure substance I is equal to the Henry's law constant I times the mole fraction of I, at least in an ideally dilute solution. Now, one thing, helium is less soluble than nitrogen, diatomic nitrogen, as you probably guessed. Now, so we have the chemical potential of I is equal to chemical potential I at standard state plus RT times the natural log of the mole fraction of I. That's for non-electrolytes anyway. And then we have ammonia plus water going to ammonium hydroxide. And NH3 is very soluble. Continuing on physical chemistry, chapter 9, we're in section 8 still. So, what we have is a graph of mole fraction against pressure. So, according to Henry's law, it should be straight. If you have increased pressure, you have increased mole fraction like this. It's a straight line. This straight line represents Henry's law. Now, what happens with hydrogen, diatomic obviously, gas, it is linear, following Henry's law, until about 200 atm, and then it curves out. And the nitrogen, it's linear to only about 100 atm, and then it curves out. Now, remember, PA is equal to XA liquid times PA star. That's Raoult's law. Now, let's look at acetone versus chloroform. Here we have pressure against the mole fraction of chloroform. Now, before we did ideally solutions, we did this already. We had a straight line going from 0 to the partial pressure of chloroform unmixed, or a straight line going from 0 to pure acetone, the pressure of acetone unmixed. And then together, you would get this curve, or actually it was a straight line. But anyway, you get this here. Now, that's the dotted line, that's the ideal. Now, the continuous line, as you can see, it curves down instead. This is called negative deviation. Now, why would it do this? The important thing, you'll notice, let's think about electronegativity. We have oxygen and chlorine, or fluorine. Those are the most electronegative elements. So oxygen has an electronegativity of 3.5. Nitrogen has an electronegativity of 3.0. Fluorine has an electronegativity of 4.0. Now the answer is going to be hydrogen bonding. Okay, continuing on physical chemistry, chapter 9, section 8. This is the end of chapter 9 here. So we showed the negative deviation when we mix the acetone and the trichloromethane, or chloroform, whatever it's called. So here's the answer. Chloroform can't hydrogen bond to itself. Or chloroform can't hydrogen bond to itself. Acetone can't hydrogen bond to itself. But the chloroform can hydrogen bond to the acetone. This dotted line between the oxygen and the hydrogen is a hydrogen bond. You see, all these chlorine atoms, they're highly electronegative. So this carbon atom in the chloroform, it ends up being highly electron deficient. Yeah, boy, that's a way to butcher that. Anyway, highly electron deficient. So this hydrogen has a partial positive charge, which is attracted to the unbound electrons into oxygen for hydrogen bonding. Now for comparison, a positive deviation is when we mix acetone and this CS2 gas, whatever it's called. So here we are. Here's the total pressure, and here's the mole fraction going from 0 to 1 of the CS2 or 0 to 1 of the acetone. Again, the dotted line is a straight line here, and this is what we had before when we had the ideally dilute solution according to Henry's law. And as you can see, it all bulges outwards, so we have a positive deviation from Henry's law. And the reason is because CS2, as you can see, is just sulfur, double bonded to carbon, double bonded to sulfur, is a straight line, it's a linear molecule, it's nonpolar. Acetone, as you can see up here, it's actually trigonal planar. But the point is it has a little bit of polarity. So when you're mixing a polar and a nonpolar substance, they don't mix very well, and that's where you get a positive deviation.